Team Elicius Energy, a spin-off from IIT Madras, has developed a high-energy density 3D printed tubular PEM fuel cell that has superior volumetric power density and low operating costs than conventional alternatives.
I am Susindran. He is Amit Bosle. So we are from Elicius Energy. We are working on a prototype called 3D printed PEM fuel cell stack. So this is the stack. So right now we are going to operate that stack. So for the stack to operate, we need to supply hydrogen at a certain flow rate, and so this is a hydrogen cylinder from which we are supplying the hydrogen to the mass flow controller. In the mass flow controller, we can set different flow rates. Right now, it is set at 3 liters per minute. So, and I am going to open the outlet, and then I will connect the flow to the humidifier. So, when we pass the hydrogen, so the voltage was 0 initially, and then it went to 15 volt, which is the voltage should be 0.9 and above for individual cell. There are 16 cells, so it is giving around 15 volt. This is an electronic load with which we can program the drive cycle and everything. So right now I am going to set a current of 0.5 amps. So when we start drawing current, the voltage will come down. So right now we are drawing 0.5 amp of current, and then the stack is giving around 10 volts of potential. So right now I am going to explain about some of the basics of fuel cells, and then I will explain how we had come up with this design. So fuel cell is a device which converts the chemical energy of hydrogen into electrical energy. So there are different types of fuel cells, in which proton electrolyte membrane fuel cell is one type. So this is the commercially available cell which is available in the market. So you can see that this is very heavy compared to this tubular cell. This is what we had developed in house. So this is a single cell comparison. So when we go for the stack, we have to go for the stack to basically increase the capacity of the fuel cell. So we had developed a stack by incorporating 16 cells, and also each cell is increased by 3 times in dimension. So you can see the 16 cells is arranged in 4 rows and 4 columns manner. So the main thing is we have to pass hydrogen for the stack to work. So we had to design a flow distribution channel which is very compact, and also it should uniformly distribute the hydrogen for all the 16 cells. So that we have come up with the design for the flow channel. So this is actually 3D printed with plastic. So you can see there is one inlet for the hydrogen, and this is being split into 4, and this 4 is again split into 16 cells, and this 16 cells is going into all the 16 cells, and there is the similar design is there in the bottom as well, and this is an exit, and this exit is being sent out to the atmosphere. This is being whatever unused gas is there, which will go.
Just to add what Susindran talked about this tubular fuel cell is basically a collection of 2 concentric tubes between which the membrane electrode assembly is wrapped around and is held tightly. And if you see this conventional fuel cell, which weighs close to 2 kilograms, whereas the same cell having or the cell having similar area close to 6 centimeters square in both cases, this weighs close to 50 grams. So you can see the volumetric and gravimetric power density of this cell that we have developed in the lab is much higher in comparison to the conventional fuel cell. Now if we come to the stack, as you can see, these cells are much elongated compared to the single cell because the area is increased here. This cell, as I mentioned earlier, is 6 centimeters square, whereas this single cell in the stack is close to 18 centimeters square. So similarly, 16 such cells are arranged in a definite order, and we have clamped this cell between the 2 plates having in gas inlet and gas exit. Yeah. Okay. So as we can see, this is the stack that has been produced and fabricated in house, and here we have made some arrangements to measure the individual cell potential So like we can see here, the cell 1 corresponds to close to 0.55 volts, whereas cell 2, if we calculate or rather measure it, it goes sorry, it goes to 0.59. So 0.6. All cells are approximately in the same, they have same or similar potential, the operating potential. Although this arrangement wasn't required, but we made it because we wanted to see the individual cell potential and to measure it as well.